Okay, 2.5 is exponential decay. Everybody hear me okay? Good. So 2.5 exponential decay. Okay, if P is equal to P naught, e to the negative KT, then the population follows an exponential decay model. Follows an exponential decay model such that dP dt is equal to negative Kp. So this is the differential equation. But this differential equation models this exponential function, okay? And notice the difference between growth and decay. So growth, population growth, was e to the KT. So notice the only difference between growth and decay, okay, this is growth, whereas this is decay, is the negative sign. That's the only difference here. The only difference between growth and decay is the negative K. Okay, so again, this guy is growth, and this guy is decay. Okay, so when we have this decay model, exponential decay, it goes down exponentially, and where we usually start at, say, t equals 0, this would be t and this would be p, okay, p versus t, this would be when t is equal to 0, that would be p naught. That's why we call it p naught, because it's p at time 0. Okay, and so generally we don't have this part of the graph. We just have the part that starts, because we don't usually go back in time and talk about what happens in previously. We just talk about what happens at time 0 and forward when we're talking about decay. Think of depreciation of a car, right? Say that you start at $20,000 for your car, and then what does it do? It depreciates and it goes down, right? So we don't talk about how much it's worth before you bought it. We talk about how much it's worth after you bought it, starting at time 0. T equals 0 is right here. Okay, okay, let's look at number 1 here, example 1. Strontium 90, whatever that is, some biology thing, okay, some isotope. Strontium 90 has a decay rate of 2.8% per year. Okay. The rate of change in the amount N of this radioactive isotope is given by dN dt equals negative 0.028 n. Okay, so what does this mean? This is, think of this as n prime of t is equal to negative 0.028 n. Okay, and when we have this, that's our exponential decay model of rate 0.028. Okay, so given this rate of decay, this is decay. How do I know it's decay? Because it's negative. It's a negative decay. Okay, so what would be the exponential decay model? Well, it's P is equal to P naught KE to the negative 0.028, that's the rate, times time. Okay. So given this, we want to know, A, how much of 1,000 grams of strontium is left after 70 years. Okay, how much of strontium is left after 70 years? Okay, so I'm going to rewrite this as N and N naught because they're using N's here. Okay, that's fine. Okay, so I'm going to plug this in. N of 70, okay, N of 70 or N of T, okay, is equal to N naught. Well, how much are we starting with? We're starting with 1,000. That's what we're starting with. N naught is 1,000. E to the negative 0.028 times how many years? Well, 70 years. Okay. So N is equal to, plug this into a calculator, and we get 140.9 grams. Okay, part B. How long will it take to have half as much strontium? To have half as much strontium. Okay, well, there is a formula for this, and that for a decay model, okay, as long as it's decaying, then the half-life, we don't call it doubling time, we call it half-life. Okay, let me put decay in parentheses. If we know it's decay, then the half-life is equal to the natural log of 2 over r. It's the same as the doubling time, but in this case, the rate, or sorry, you know what? It's not 2. It's 0.5. My bad. Okay, it's the natural log of 0.5 over r, where r in this case is negative now. It's a negative rate. It's a decay rate. So we need to make sure that r is negative. Okay, we could put the negative in here if we wanted to. Okay, or just to remind us that, hey, it's a negative rate. If r is 0.028, then it's a negative rate. It's a decaying. Okay, so this is your half-life formula. Now, we could verify that this is the half-life formula by doing a little bit of algebra. We can see, oh, okay, where did this come from? Well, if I want half as much, well, what's 1/2 of 1,000? Well, isn't that 500? So I want to end up with 500. Let's look at the formula again. N is equal to N naught E to the negative RT, right? Okay, or KT, I don't know which one I used here. Okay. Maybe it was K, R, whatever. Doesn't really matter. Okay, let's let it be R. Okay, and so we're going to have 500 is equal to 1,000 E, okay, to the negative rate. Well, what's the rate? It's negative 0.028, okay, times T. Well, we don't know what T is. That's what we're looking for. We're looking for the half-life. How long is it going to take to have half as much? Okay, so let's divide by 1,000. And we're going to get 0.5 is equal to e to the negative 0.028t. Now, how do I undo the exponent, the natural exponent? I have to natural log it. I'm going to take the natural log of both sides. And those are going to cancel out, and I'm left with the natural log of 0.5 is equal to negative 0.028 times t. And now what I'm going to do, I'm going to divide by negative 0.028. And I'm going to get t is equal to natural log of 0.5 over negative 0.028. So we can see that if we plug that into a calculator, we would get approximately 24.76 years. Okay, so it's going to decay to half, the half-life. Okay, the half-life of this thing is 24, almost 25 years. Okay, and so you don't have to go through this whole process, okay, each time. Okay, you can kind of skip this if you just know the formula here for half-life. You can go directly from here down to here. Okay, but I wanted you to see how it works at least once. Okay. Sorry. Okay. Let's move on. Okay, let's do let's talk about present value. Okay, how can I find present value? Okay, calculate present value. Okay, calculate present value for continuously compounded interest. Okay, so how do we find present value for continually compounded interest? Okay, how are we going to do that? Well, here's the deal. Okay, what was the formula for continuously compounded interest? Wasn't that the PERT account? A equals P e to the RT. And what did we say P was? What did we say P was? Okay.
Principal.
Isn't P? Oh, Gabriel says, what if the base wasn't E? Could you still take the natural log? Yeah, you could take the natural log of any base. Okay, and then you would just bring down the exponent. Okay, Gabriel? Okay. Okay, for this one, what was P? What did we call P here in our formula? Anyone remember? Okay, how about principal? Principal, or yeah, the amount invested. Thank you, Oscar. Okay, you can think of it as principal or present value, right? Isn't that really my present value, how much money I have on hand today, right? That's the present value or the principal, either way. So what I'm going to do here is I'm going to solve for principal here. I'm going to solve my equation for P. So how would I do that? How would I solve this equation for P? Well, P is being multiplied by e to the RT, right? So couldn't I just divide both sides by e to the RT? Okay. Yeah, let's do that. Okay, so P is equal to A over e to the RT. And I could leave it like that, but that's not how we leave it. Okay, we can make it a little bit prettier, make it look like a formula that we've already used. Why? Because 1 over a positive exponent is the base raised to a negative exponent. Isn't that right? So couldn't I just make this negative RT? Couldn't I say P is equal to A E to the negative RT? And look at that. That's my exponential decay model. So if I want to find the present value, I can use an exponential decay model. Kind of cool. Okay. Okay, let's look at an example here. Okay, example 2 from business. Okay, no more of this strontium stuff. We're not biologists here, are we? Anybody in here a biology major? Okay, the grandparents went to invest. Okay, the grandparents of a child wanted to invest money so that at 4%, their grandchild would have $10,000 on their 20th birthday. How much should be invested today? Be invested, we'll say invested at birth. Okay, not at the birth of the grandparents, because that wouldn't work here. At the birth of the child. Okay, so at the birth of the child. So we're just saying that it's going to be 20-year investment. That's all that means. Okay, so we want the present value. The present value is going to be equal to the future value. I'll just say, hey, the present value is going to be equal to future value times E to the negative RT. Okay, present value is equal to future value E to the negative RT. Okay, so what do we want? We want the future value to be 10,000. We want the rate to be 4%, and the time is going to be 20. So all I do is plug this in. Let me do that real quick. Okay, let's plug it in. Okay, so we're going to say 10,000 times E raised to raised to the negative 0.04 0.04 negative times 20. I should really have a parenthesis there. Let me put a parenthesis there. Okay, negative 0.04 negative times 20. Okay, so that's 0.8 equals, and I'm getting $4,493.29. So $4,493.29, or I would say roughly $4,500. So invest your $4,500, grandpa and grandma, and you're going to have $10,000 for your grandchild in 20 years. Okay, so you'll make more than double your money in 20 years. Okay. Okay, last topic for tonight is 2.6. Okay, derivatives of a to the x and log base ax. So I'm sure Gabriel is going to like this one, because it's like, well, how do we take derivatives of things that aren't base e or aren't natural log? right? What do we do there? Right, okay, so let's take a to the x, right? A to the x, what would that be like? That would be like, hey, derivative of 2 to the x power. How would I find the derivative of 2 to the x power? Well, we actually do this a little sneaky. We're kind of sneaky about it. If we wanted to find the derivative of this, I'd have to use the property of logs. Okay, and this is what I would do here. I would say natural log y is equal to the natural log of 2 to the x. Okay, and I know that now I can bring this down and put it in front. So that's natural log y is equal to x times natural log 2. Okay. Okay, now what I'm going to do is I'm going to take the derivative of both sides. Both sides. Take the derivative of both sides. Well, the derivative of a natural log is just 1 over that value. So this is 1 over y. Okay, and then I'm going to put a y prime. Because I took the derivative of y, which is y prime. Okay, I just got to keep that in mind, in my back of my mind. That's y prime. And then the derivative of natural log 2x, well, this is just a constant times x. So that's just natural log 2. Oh, okay. So if I were to multiply both sides, this is the sneaky part. If I were to multiply both sides by y, that would cancel out the y values. And I get y prime equals natural log of 2 times y. But what was y? Y was just 2 to the x. So this becomes y prime equals natural log of 2 times 2 to the x, or y prime is equal to 2 to the x natural log of 2. Now, the great thing about this is you don't have to memorize any of this, none of it, okay? All you have to do is memorize the formula, okay? d dx of a to the x, any number to the x power, is equal to a to the x itself times the natural log of a. That's it. That's the derivative. It's that easy. That easy. Okay, so let's do a couple of problems with this formula here. Okay, number 1. Okay, differentiate okay, a, y equals 2 to the x. Oh, we just did that, right? We just did that the long way. So let's do it the short way. Y prime is equal to 2 to the x natural log 2. Boom, done. That was easy.
That was easy.
There you go. That ain't my easy button. Okay. That was easy.
That was easy.
Exactly. Okay. Let's do B. Okay. Y equals 1.4 to the x power. Okay, so 1.4 to the x power. Again, super easy. Let's use the formula. Y prime equals 1.4 to the x power, natural log 1.4. That's it, done. Okay, let's try a chain rule here. Let's do the chain rule. Y equals 3 to the 2x power. Let's do the chain rule. So y prime is equal to, what's y prime? Y prime was a to the x natural log a, right? Okay. Okay, so this is going to be the original expression, 3 to the 2x, okay, times the natural log of 3, right? But the x was a function. So we have to take the derivative of this thing now to do the chain rule. This is my u. Okay, u is equal to 2x. So du is equal to 2. Okay, so I've got to multiply by the 2. Okay, the derivative of the exponent. Multiply by that 2. Don't forget to multiply by that 2 because this is a chain rule. So this is going to be y prime equals 2 times 3 to the 2x times the natural log of 3. Okay, okay, number 2. Okay, how do we take the derivative of a log that is not base e? So we'll say log base 2 of x. How do we find the derivative of this? Well, I'm not going to go through how to do the logs. It's very much like we did before, where instead of taking the natural log to both sides, we would raise it to the e power. Raise both sides to the e power, and then we turn it into an exponential. Okay, but this is going to be equal to, okay, 1 over, okay, x times the natural log of 2. That's it. Oh, that's all it is. Okay, if you had natural log of x, right? What was d dx natural log of x? Wasn't that just 1 over x? So here you just have this natural log of whatever the base is, okay, on the bottom. That's it. Pretty easy. So if we wanted to generalize this, this would be log base a of x is equal to 1 over x natural log a. That's it. Boom. That's the derivative of that guy. Okay. So let's do an example here. Okay, number 2. Okay, differentiate. Okay. A, y equals log base 8 of x. Okay, so what is this going to be? This is going to be y prime is equal to 1 over x natural log 8. That's it. Boom. Easy. Okay, what about b? B is equal to y to b or not to b? That is the question. Okay, in front of us. Okay, log base 3 of x squared plus 1. Okay, this is going to be y prime is equal to 1 over whatever this is after the natural log, or sorry, after the log. That's 1 over x squared plus 1 times natural log of 3, that's the base, times the derivative of x squared plus 1, which is 2x. Why? Because it's a chain rule. It's the derivative of the outside times the derivative of the inside. Well, what's the derivative of the inside? The inside is the x squared plus 1. So that's a 2x. So we've got y prime is equal to 2x over x squared plus 1 natural log of 3. Oh, okay, pretty cool. Okay, and C, y equals x cubed log base 5 of x. Okay, this is going to be a product rule because we've got a function of x and a function of x. So we're going to say y prime is equal to the derivative of the first, it's 3x squared, times log base 5 of x, plus derivative, or we'll say the first times the derivative of the second. Well, what's the derivative of log base 5 of x? That's 1 over x natural log 5. Well, one of these x's is going to cancel with one of these x's, and it's just going to leave me with x squared. So y prime is equal to 3x squared log base 5 of x plus x squared over the natural log of 5. Boom. Okay. Okay. Number 3. Let's talk about what an annuity is. Okay, this is business example. Annuities. Okay, an annuity is a investment that pays you out in increments. Okay, say that grandma has invested $100,000 in her retirement account. She's not going to take all that $100,000 out of her 401k. she's going to take it out in payments, right? She doesn't want to take it all out at once because it's not making her money. But if she can take that out in payments, right, then her money will last a lot longer because that money that's staying in the bank will make interest. And that's what an annuity is. You just take the money out incrementally. Okay, so a savings account that has regular deposits or withdrawals of equal size is called an annuity. Okay, if we have for deposits, if we say that we deposit money periodically, we're building this up. Say we're building our fund up, our retirement fund up. We deposit monthly into this retirement fund, so we're building it up. Okay, if we're depositing regularly, okay, for deposits, then the accumulated value is equal to the deposit. I'm going to use D for deposits. The deposit amount times 1 plus R over N to the NT minus 1 all over R over N. Okay, so this is for deposits. Okay. Okay, so deposits is this. For withdrawals, it's a little different. Okay, it's A of T, the amount after a certain amount of time. Okay, A of T is equal to the monthly withdrawals. And then these are kind of reversed. It's 1 minus 1 plus R over N to the negative NT all over R over N. Okay, so deposits, if you're building money, this is growth. If you're taking withdrawals out, that's decay. This is also for loans, by the way. Loans work as a withdrawal annuity. Why? Because the payment that you're paying to that thing a month takes down the balance in your account. Right? That's the balance you owe. Right? So it works, the withdrawal annuity works mathematically the same as a loan, like a car loan. Okay. Okay, so let's do one last example here. Okay. So if I deposit $150 okay, a month, at 6% interest, what is the value of the annuity? The annuity after 5 years. Okay, so let's write our formula down again. A of T for deposits, right, is equal to D times 1 plus R over N to the NT minus 1 all over R over N. Okay, so we're just going to plug in. Okay, so I have 150, right? So 150 times 1 plus this is 0.06 over 12 to the 12 times 5, so that's 60, minus 1, all over 0.06 over 12. Okay, so let me clean this up a little bit. This is 150 times, okay, 1 plus, or 1.005 to the 60th power minus 1. Okay, times, I'm going to say that this is times 12 divided by 0.06. Okay, or I don't really have to. Okay, I can just say divided by 0.005. Okay, and if I were to plug this into a calculator, I would get approximately 2421. Sorry, not 2421. I would get approximately 10,465 and 50 cents. Okay, after 10 years. Or sorry, after 5 years. Okay, so how fast is this changing at the 5-year mark? Let's call this part A. Okay, A. Let's finish this up with part B. Okay, so if I deposit $150 a month for 5 years at 6% interest, I will have $10,000, $10,465 in the bank at that time. Okay, so part B is how fast is the account growing? How do you spell account? Account growing at the 5-year mark. Okay, how fast is it growing at the 5-year mark? Okay, so okay, we need to take and find out, well, what's A of t? A of t, okay, is going to be that 150 times 1 plus 0.06 over 12 to the, what was that, nt, so this is 12t minus 1 all over 0.06 over 12. Now, the one thing that I don't, put in, okay, is t, because t is the thing that is changing. Okay, t is the thing that is changing. So I do not plug in the 5 right now. I wait until after I take the derivative. Once I take the derivative, then and only then do I then substitute in for t. Okay, if I don't take the derivative, then all I've done is substitute in for the 5, and it will give us the exact same answer we got before. Okay, but now that I have this in this form, and I might clean this up a little bit more. I might go 150 times 1.005 to the 12t, okay, minus 1. And then I'm going to do this. I'm going to go times 12 over 0.06. And what is 12 divided by 0.06? 12 divided by 0.06 is 200. So this thing becomes 200. 200 times, so this thing becomes 200. 200 times 150 is 30,000. So this is really 30,000 times 1.005 to the 12t minus 1, and I could distribute that 30,000. Okay, I'm just wanting to get it into a form that's nicer to differentiate. So I get A of t equals 30,000 times 1.005 to the 12t minus 30,000. Okay. So now let's take the derivative of this thing, a prime of t. Okay, the derivative of the constant is going to go away. That's 0. Okay. This thing is a power, is a base to a power, base to a power. Oh, okay, well, this is just going to be 30,000 in front. And then what was the formula for a base to a power? How do we find the derivative of a to the x? Well, wasn't it a to the x natural log a? Yeah. So this is just going to be 1.005 to the 12t times, okay, times the natural log of 1.005, okay, times 12. Now, where did that 12 come from? Yeah, that 12 came from the natural log, right? I mean, sorry, from the exponent, from the chain rule, right? Yeah, it's the derivative of u. It's the 12t, the derivative of 12t here is 12. Okay. So now let's clean this up a little. What's 12 times 30,000? That's 360,000, right? 360,000 times the natural log of 1.005. Okay, now I have a prime of t. Okay, times that. Okay, times 1.005 to the 12t. Now I can plug in 5. Once I have the derivative, now I can plug in 5 to get the rate of change at the 5-year mark. So 360,000 times the natural log. Is this the natural log of? Yeah. Let's see how did I go wrong? Where did the? Oh, you know what? No, that's right. Yeah. It's true of that. Yep. Yeah. Makes sense. Yeah, natural log of 1. Okay, yeah, perfect. Okay, so natural log of natural log 1.005 times 1.005 to the 12 times 5. Well, what's 12 times 5? Isn't that 60 to the 60th power? Yep. Okay, so what is this going to be equal to? Well, let's plug this into the calculator real quick. Okay, clear. I'm going to take 360,000, okay, times the natural log of 1.005. So 1.005 natural log, okay, times 1.005 raised to the 60th power. Boom, and I get 2,421.88. Okay, and what does this mean? What does this mean? It's just some number, right? It means that, let's write it out all as a sentence. At the 5-year mark, the fund, or the account, has grown to $10,465.50 and is growing at a rate of $2,421.88 per year. Now, why is it year? Because our interest rate is yearly. Okay. Okay. I mean, we do a monthly thing, but we're talking our time is in years. Okay. And that's what that means. And that's it. That's the notes for today. So I'm going to post. That's it for chapter 2. I'm going to post the study guide as well tonight, and then we'll review Tuesday, and then we have an exam Thursday, I believe. Okay.
Yes, sir. You show me
We
the.
got. I don't know. We have more. We have more. This is just Tuesday. No, we're meeting Thursday, and then I think a week from Thursday we have a little bit more lecture on Thursday. And then Tuesday is review, and then next Thursday I believe is exam. I think. Is that right? No, next Tuesday is exam. Sorry, I'm ahead of myself. We will review on Thursday, and then the exam will be next Tuesday. That's right. I was thinking the exam was Thursday, but it's Tuesday. I will post a review right now, and then we'll be going over any questions on the review on Thursday. Okay. Deposit and withdrawal formula, sure. Okay, and keep in mind that all the lectures are on YouTube as well. So if you ever miss anything, you can always go back and get them off of YouTube, my YouTube channel. Okay. Thanks. See you later. See you Thursday. While you're doing that, I'm going to post the study guide. Okay. Yeah, sounds good. Real quick.